If you step on a bug in the Jurassic period, you alter the outcome of human evolution. We've all heard the premise. In popular culture, the butterfly effect is treated as a chain reaction where one microscopic event dictates the entire course of history. The most famous phrasing of this comes from a 1972 academic talk, which asked a seemingly absurd question. Does the flap of a butterfly's wings in Brazil set off a tornado in Texas? People tend to visualize the insect's wings acting like a tiny fan, generating a miniature breeze that gathers strength across the ocean until it physically spins up a catastrophic storm. The Earth's atmosphere is viscous. The friction in the air would dampen out a microscopic disturbance from a 1-gram insect in a matter of seconds. The butterfly does not power the storm. With the physical butterfly ruled out as a power source, we have to look elsewhere for the cause of the storm. The true butterfly effect describes a specific vulnerability in how we model and understand the world. The pioneer of chaos theory, meteorologist Edward Lorenz, didn't even use a butterfly in his original analogies. When he first presented this concept, he suggested that one flap of a seagull's wings could alter the course of the weather. Colleagues persuaded him to make the title of his 1972 talk more poetic. The seagull was swapped out for a butterfly, and that single rhetorical choice permanently skewed how the public imagines chaos theory. Lorenz only ever meant for the animal to serve as a metaphor for a tiny, unmeasurable discrepancy in starting data, what mathematicians call a change in initial conditions. It's a way of illustrating that if you run a mathematical system twice, and the starting numbers differ by a fraction of a percent, the final results will eventually become completely unrelated. By obsessing over the physical insect, we missed the actual warning. Lorenz was demonstrating that the future is intensely sensitive to details we simply cannot measure. Lorenz stumbled onto this reality by accident in 1961 while running numerical weather simulations at MIT. He was using the vacuum tube computers of the era to mathematically model the atmosphere. These machines were massive, slow, and relied on manual data entry. Trying to save time, Lorenz decided to restart a simulation from the middle. Instead of typing in the full precision value of 0.506127 from the machine's memory, he entered the rounded number from the paper printout, 0.506. He expected the new run to duplicate the old one. But when he returned from getting coffee, the simulated weather had separated entirely from his previous run, producing completely alien storm patterns on the screen. A difference of less than 1 part in 1,000 had compounded rapidly. Lorenz proved that even in a deterministic universe, where you know the exact equations, the tiniest measurement error destroys the accuracy of any long-term forecast. Mathematicians call this mechanism sensitive dependence on initial conditions, or SDIC. It is the engine driving chaos theory. This animated graph is the Lorenz attractor. If you place 2 dots at nearly identical starting coordinates, representing 2 weather systems with a microscopic temperature difference, they initially trace the exact same shape. But as the system evolves, a process of stretching and folding occurs. The paths diverge at an exponential rate, drifting further apart with every loop they make. In meteorology, that tiny initial discrepancy doubles every few days. Eventually, one path represents clear skies, while the other, now orbiting an entirely different region of the graph, represents a severe storm. Because of sensitive dependence on initial conditions, a system governed by fixed, simple rules eventually becomes observationally indistinguishable from a purely random one. When you map that abstract math onto the physical scale of the Earth, the problem compounds. The atmosphere is a chaotic fluid covering an entire planet. To perfectly predict tomorrow's weather, you would need to measure the temperature, pressure, and humidity of every cubic inch of air with infinite decimal precision. Missing a single gust of wind ensures your eventual prediction will fail. This forces a boundary on our capabilities. Atmospheric predictability hits a wall at roughly 2 weeks. This is why meteorologists rely on ensemble forecasting. They run multiple models with tweaked starting data, generating a spread of paths to account for chaos. The butterfly effect is not an engineering problem that can be fixed with better sensors. It is a physical boundary defining what is actually knowable in our world. This rule governs every complex system. From the spread of a pandemic to the dynamics of global economics, sensitive dependence strictly limits our horizon. Throwing infinitely more computing power or advanced AI at the problem doesn't bypass the math. The exponential growth of microscopic measurement errors always outpaces our processing speed. The butterfly metaphor survives as an illustration of the fragility of our foresight. We like to imagine the universe as a predictable clockwork machine, where precise inputs yield easily calculable outputs. The reality is deterministic, but intensely chaotic. Edward Lorenz's pioneering work provides a rigorous mathematical proof that the distant future will always remain inherently unknowable.